All right, we are going to talk about the alternating series estimation theorem, which we introduced when we introduced the alternating series test for convergence, only because they are related. But this is really a preview of what's to come later on in the unit when we talk about error in our estimations of the value of a series. So let's talk about an alternating series. As we learned on a prior page, if we were to approximate, for example, the alternating harmonic p-series, if you recall, we started at 1, then we toggled back to 1/2, and then we went up to 5/6, and then we went down to 7/12, and then up and then down, up and down, and the real value was somewhere in the middle between the last two terms, because if you subtracted the last term, it would be an underestimate of your actual value. And if you had added the last term, it would be an overestimate of your actual value. So this is your little visualization of explaining that. So what we actually are going to talk about today is how we can estimate the sum of a series using the alternating series estimation theorem, which means that we add a certain number of terms in the series, and then the error value will be the absolute value of the first unused term. So let's talk about what that means. This is the alternating series for 1 over n squared. We're multiplying using the alternator of -1 raised to the n plus 1. And we can approximate it to an error of 0.01 by adding together, looks like I'm adding together 9 terms. So 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared, all the way up to 1 over 9 squared. So I've added 9 terms, and I get, when I put this in my calculator, 0.828. Well, the first unused term, after I add 1 over 9 squared, I will be subtracting 1 over 10 squared. So that's -1 over 100. So the error in the estimation is, like I said, the absolute value of the first unused term. So the error in my estimation is 1 over 100, which is 0.01. Now, to be clear, that is the maximum possible error, because we know that's not the exact error, because once I add that next term, or actually subtract this term of 1 over 100, that means that the next term added would be plus 1 over 121, and that is less than a value of 0.01. So 0.01 is actually too big of an error. But what's really cool is that I'm only taking 9 terms here, and I'm getting my sum to within 1/100th. Now, why does this help us? Well, it helps because I can only take the sum of a convergent geometric series or a telescoping series. And we've mentioned that we really don't use telescoping that often. So if we don't have a convergent geometric series, we can't find the sum. But if we have an alternating series, we can add together a certain number of terms and come to a fairly small error within the actual value, even though we don't know the actual value. So here, since I have 0.828 as my estimation, and my next term would have been subtracted, that means my actual value is going to be between 0.818 and 0.828. And the reason why I know that it's going to be on the smaller side is that my next term would have been subtracted. So I would have had to bounce to the left on the number line. So I would never have been greater than 0.828 because my next term was not going to be added. So that's a pretty small interval on which I know my sum must be. So let's talk about how we can use our calculator to help with this. Let's put this into our calculator. So I'm going to go to my TI-89, and I am going to clear out everything that I had. So start a new problem, hit enter twice, and now I'm going to go to F3, choice 4, which is sum, and I'm going to plug in -1 raised to the, and put in x plus 1 in parentheses, x plus 1 in paren, and then multiply that by, in parentheses, 1 divided by x squared. And then I think you need to close parentheses. Let's see, we opened once, closed, opened, closed, opened, closed. I should just be able to put in a comma. X to tell it that the counter is X. And then 1 to 200 tells it to count the first term through the 200th term. So I'm adding up the first 200 terms here. And I think I'm going to get a fraction because my calculator is set to auto. And this is going to take it a moment. And that fraction is crazy, so I'm going to swing up and grab it and bring it into my row, and then hit green diamond enter. And it's going to convert it to a decimal, and it tells me that the decimal approximation is 0.822. So that means that if I add up the first 200 terms, I'm going to get an estimate of 0.822. Notice that that estimate is in between the lower limit and the upper limit, or the lower bound and the upper bound I had for my sum previously. And so what is the error in the estimation? Well, it's going to be 1 over the 201st term. So, well, not 1 over the 201st term. It's going to be the absolute value of the 201st term, which is 1 over 201 squared. So if I go back to my calculator and I do 1 divided by 201 squared, and I'm going to hit green diamond enter to give this a decimal, the error in my estimation is 4 zeros and a 25. My error is 0.000025. Now that is a tiny error from just adding up 200 terms. All right, let's try a problem, and I'm going to clear out what I had on my screen because this is going to be a calculator problem. And they want to know how many terms are needed to estimate this series with an error of less than 0.001. Well, the error term is whichever term is going to be less than 0.001 in absolute value. So what I can do is ignore the -1 to the n plus 1 and just look at the 1 over n to the 4th. And in my TI-89, I can say 1 divided by, and I'm going to go ahead and use x because it's a bit easier for me right now. And if I do a such that key, let's do this such that x equals, say, 3. So this would be the third term is 1 over 81, which is not less than 0.001. So the third term is not my error term. And then it's just a bit of guess and check. I'm going to change this to a 4. I'm going to hit green diamond enter to make it a decimal place. So the fourth term is not small enough to be my error term. So then change it to a 5. Make sure you hit green diamond enter. Okay, I'm getting closer, but still the fifth term is not my error term because it's bigger than 0.001. So try the sixth term, green diamond enter. Ah, this one, the sixth term, is my error term because it is less than 0.001. So the question was, how many terms did we need to add to estimate with an error of less than 0.001? Well, if the sixth term is my error term, and I started at the first term here, n equals 1, then I needed to add 5 terms to get an error of less than 0.001. And then my last question on this topic is, let's approximate the sum of this series to 4 decimal places. So for this one, let's go ahead and clear out our calculator, start a new problem, and then I'm going to actually put this series notation in my calculator. So I'll go to F3 and then choice 4 for summation, and I'm going to put in parentheses and then -1 raised, oops, lost my second parentheses, close parentheses, raise it to, in parentheses, x plus 1, and I'm using x instead of n, and then divide that by, open parentheses, and put in 2x, close parentheses, and then for factorial, you want the green diamond division sign. It doesn't say that that's factorial, but I promise it is, green diamond division sign. And then, of course, you need comma x to tell it that x is your counter, comma 1, and then let's just add up, say, the first 2 terms. Seems like a good place to start. So 11/24. So now we need to continue to add terms, so we're going to come back here and we're going to change this 2 to a 3. So this expression now adds the first 3 terms of this series. I'm going to use my green diamond key, and I have here decimal place accuracy. And so now I'm going to change it to adding up 4 terms and using my green diamond. So 4597, 4596, my 4th decimal place is still not the same, so I need more than 4 terms. So let's change this to the 5th term. Green diamond, enter. 4596, 4596. So actually when I added just 4 terms, I got 4 decimal place accuracy. And the sum of this series is 0.4596. And yes, I do realize that you could have rounded it to 0.4597, but this will be 4 decimal place accuracy, and you needed 4 terms to get there. They didn't ask how many terms you needed, but I thought that would be helpful.